now let's talk about the area in all three coordinates. So first, let's talk about an easy one, the area in rectangular coordinates. That means the sum of the sigma from A to B. Here's a graph, and this curve is fx. So if we want to know the area between A to B, actually we can take a sigma between A to B. And I take sigma here. Of course, you can take sigma anywhere. And let's think about the area about the sigma. So what will be the area of this rectangle? As they thin as they possible, that will become a rectangular. So the area will become 2 thickness multiply height. And what is the area of this curve from A to B? That will become too many of the sigma, add them together. So the formula of the area in rectangular coordinates will become to from A to B fx multiplied dx. Okay, now let's talk about parametric coordinates. That means the sum of the sigma from T1 to T2 actually is same as a rectangular one, but we have to do a little bit transform. The first, we have to let fx equal to yx and set yx equal to yt, x equal to xt. Then dx equal to dx dy dt multiply dt. Actually, they're the same as dx equal to dx. But what we need to do, we have to put one dt out. So that's the reason why we set it like that. And then we have to put all equation back to the formula. What's the formula of the rectangular? That is from A to B fx dx. So since we put all those equations back to the rectangular one, that will become to from T1 to T2 yt multiply x derivative multiply dt. Okay, then before we talk about the polar coordinates, let's go back to the polar coordinates and the relationship between rectangular. As we can say, if it's a rectangular coordinates, it's easy to figure out here is a pxy, and it's easy to figure out here is a x and here is a y. But in the polar coordinates, we said here is r and the angle is theta. So in polar coordinates, the relationship between rectangular coordinates that will become to x equal to r cosine x and y equal to r sine theta. Okay. So the area of the polar coordinates will look like that. Of course, we also have to take a segment in here in the area. But the interesting thing is the polar coordinate segment is a little bit different between parametric and rectangular one because it's no more longer seems like a rectangular or a line. It's more like a triangle. So what is the area of a triangle? That will be half multiplied base and height. And in this case, what is the height? The height is r is radian. And the base is gonna be r multiplied d theta. So, as we know, the area of the polar coordinates will become to a equal to half multiply from theta 1 to theta 2, that's a range, and multiply r squared, actually it's r multiply r d theta, so we just put r together, that become to r squared multiply d theta. Okay, now let's do some example. So in example 1 said, under the y equal to 4 minus x squared in the interval from 0 to x less than 3. So since you saw this question, what do you think about? Of course, it's the area of the rectangular coordinates, right? So we put the equation here. But we have to remember that in the rectangular one, we'd better to draw a graph in case the area is in the negative axis. So here is the graph. We can see that from the 0 to 2 is positive area, but from 2 to 3, the area is negative. So we have to separate them and put the equation into the formula. That will become to from 0 to 2. We put the equation into the formula. Here is the fx. So that becomes 0 to 2, 4 minus x squared dx. And minus, because this area is negative, from minus 2 to 3. And 4 minus x squared dx. After that, we just have to integral them, and the final solution becomes to 23 over 3. Okay, so now let's take a look about another one. That's under half arc of a cycloid. Okay, so in this case, the formula of cycloid is x equal to r theta minus sine theta, y equal to r 1 minus cosine theta. We all know about that. And one arc of the cycloid is when theta equal to pi. So in this graph is from the 0 to 2 pi. But now we just want to figure out half. We just want to figure out the half of it. So that will become to 0 to pi. Okay, so actually before I do this problem, I was thinking, okay, this is about polar coordinates. But after you do this step, like we separate the formula to the x equal to r multiply theta minus sine theta, y equal to r 1 minus cosine theta. Actually, we had to use the parametric coordinates. And now we just put the equation into the formula. That will become to r 1 minus cosine theta multiply r 1 minus cosine theta. Because after you derivative the x, r multiply theta minus sine theta, that will become to r 1 minus cosine theta. And we just do the integral, and finally the equation's solution will become 3 over 2 pi r squared. And then let's take a look about the example 3. They said find the area inside R1 equal to 2 and outside R2 equal to 2 cosine theta from 0 to pi. Okay, here is the equation of this one. There's no any other question about like why we use this, right? Because it's so obviously we had to use the polar coordinate. And here is a graph. So we want to know this area from 2 to 2, and outside is, we want to know the difference between those two r. So in the equation, actually we just put r1 and r2 in here. It's gonna be half from 0 to pi and r1 squared minus r2 squared d theta. And then we integral them, and then the final solution will be pi. Okay, now let's go back to the rectangular, parametric, and polar about the area. So for the rectangular one, it's very easy. If we just think about as thin as we can to take the sigma, that will become to a rectangular. And a rectangular of the sigma, that will be the thickness multiplied height. So the total area of that will become from A to B. That's a range of the curve fx and multiply dx. And for the parametric one, that will become to t1 to t2 yt multiply x derivative multiply dt. And then for the polar one, you still remember the relationship between rectangular and polar? Yes. So the polar one will become to half of the theta 1 to theta 2 r squared d theta. And the reason why here is 1/2 is because the polar segment gonna looks like a triangle. Okay, thank you guys.
I shall now discuss arc length. To begin with, rectangular arc length. So say you have this graph here, and you want to find the length of this curve, AB. Now, you could use Pythagorean theorem to find the length of this curve here, and by doing so, you would end up with the equation square root of delta x squared plus delta y squared. This equation here turns into the square root of 1 plus delta y over delta x squared times delta x. Now, the Pythagorean theorem leaves you up to a good amount of error, as you are not covering the entirety of the curve. You're either above or below the curve in your equation. So, how do we solve this error? We take delta x and we make it smaller. This reduces the error. And as delta x approaches 0, delta y over delta x approaches dy over dx. As a result, we can use integration to get the length of the curve. Thus, the arc length of this curve is the integration of square root of 1 plus dy over dx squared dx. Now, parametric arc length. So say you have a curve that is parametrized in the form x equals f of t, y equals g of t, and t is between alpha and beta. You can assume that this curve is going to be traced out left to right and will only be traced out once as t goes from alpha to beta. So, in short, d of x over d of t is greater than or equal to 0 for t between alpha and beta. Now, what we need to do is recall the previous equation for rectangular and its different forms, depending on whether or not it is y equals f of x or x equals f of y. You also need to know that d of x equals f prime dt, which is equal to d of x over dt dt. The formula then becomes the integration from alpha to beta, the square root of 1 plus dy over dt squared divided by dx over dt squared, dx dt outside the square root, dt. Then you factor out the denominator from the square root, which gets you this equation here. And by canceling out the denominator, you get the equation for the arc length of parametric equations, which is integration from alpha to beta, the square root of dx over dt squared plus dy over dt squared dt. Now, polar coordinate arc length. So, this means you are given a curve in polar coordinates, meaning that r is going to equal f of theta, and theta will be between alpha and beta. So, we shall now write the curve in terms of a set of parametric equations so that we can find the equation for arc length in polar coordinates. So, x equals r cosine theta and y equals r sine theta. Here are some derivatives that we will need for computing the length of the curve. And by applying it and referencing the previous parametric equation for arc length, we get dx over d theta squared plus dy over d theta squared equals dr over d theta cosine theta minus r sine theta squared plus dr d theta sine theta plus r cosine theta squared, which expands out and gets very nasty, but then simplifies back down to dr over d theta squared cosine squared theta plus sine squared theta plus r squared cosine squared theta plus sine squared theta, which simplifies even more down to r squared plus dr over d theta squared, or if you prefer, instead of dr over d theta squared, r prime squared. This is what we were looking for, and now we plug it back into the parametric equation for arc length and find polar coordinate arc length, which is integrate from theta 1 to theta 2, the square root of r squared plus dr over d theta squared d theta. Now, an example. So say you have a parametric equation of x equals t and y equals 1/2 t squared for t between 0 and 1. So what we do is we find x prime and y prime, x prime being 1 and y prime being t. Now we just apply the formula that we know for parametric equations, and you get the integration from 0 to 1, the square root of 1 plus t squared dt. Now, what we do is we substitute t equals tan of u, and u equals tan inverse t, and dt over du equals secant squared u. Now we just plug that in, and it solves out to integration of secant cubed u du. Now we solve for the integration of secant cubed u, and then plug back in the u equals arctan t to get ln equals the square root of t squared plus 1 plus t over 2 plus t square root t squared plus 1 over 2. Now that we have the answer, we plug in the numbers, and we get the answer of approximately 1.15. Now, another example, but with the same equations. This time, however, it is in polar coordinates. So, we start by finding r. So, we know that r squared equals x squared plus y squared, which equals t squared plus 1/4 t to the 4th. r, therefore, equals 1/2 the square root of t squared times 4 plus t squared. Now we need to find t, so we find y over x equals tan theta, which equals to t over 2. T therefore equals 2 tan theta, and dt d theta equals 2 secant squared theta. Theta therefore equals arctan t over 2. Now that we know what t is equal to, we plug that into r, and find that r equals 1/2 the square root of 4 tan squared theta, 4 plus 4 tan squared theta, which simplifies down to 2 square root of tan squared theta secant squared theta. Then you find r prime. r prime equals 2 tan theta secant to the 4th theta plus 2 tan cubed theta secant squared theta divided by the square root of tan squared theta secant squared theta. Now we just have to apply the formula for arc length in polar coordinates to get a nice and long equation. This equation simplifies down to 2 times the square root of secant to the power 6 theta times 3 sine squared theta plus 1 d theta. We are going to now take the secant power 6 theta out of the square root, and we are now going to substitute the theta and the dt over d theta values into this equation. It gets us the equation of integration of 0 to 1 square root of 3 over 2 t squared dt. This solves out to the square root of 3 over 4.
Let's take a look at surface area. As we all know, there are two situations for surface area, which are around y-axis or around x-axis. No matter how to rotate it, the first thing we should do is take a sigma. When we rewrite it, it becomes a circle. As we all know, the formula of disk side area is 2 pi rh. When we rotate the sigma, r equals to x and the height becomes arc length. So we can rewrite our formula as s equals to 2 pi integral c to d x times square root of 1 plus dx over dy squared dy. Also like this one, when we rotate this sigma, the r becomes to y, and the height also the arc length. So we rewrite the formula like this one. Since we have 3 different ways to find the arc length, we also have 3 different ways to find the surface area. These 2 are the rectangular form, and these 2 are parametric form. In polar form, everything seems to be different because we got r cosine theta and r sine theta. This graph is an example of r equals sine 3 theta. Let's say we want to rotate around pi over 2 axis. First thing is find the sigma, which is this horizontal line. Then we rotate it around y-axis, which is this circle. And next step is find the r, which is r cosine theta. Since we know the arc length, so we can write the formula as 2 pi r cosine theta times square root of r squared plus dr over d theta squared d theta. Same way goes to when rotating around the polar axis, rotating of this sigma, which is r sine theta. Let's take a look at this example of rotation around the x-axis of y equals 1 over x, which x bigger than 1. The first thing we should do is write down the formula. S equals 2 pi integral fx times square root of 1 plus derivative fx squared dx. When we put a number we have right now, the formula becomes 2 pi integral 1 to infinity of 1 over x times square root of 1 plus 1 over 4 square x 4 square dx. And here is how to solve the derivative fx. Since it's hard to solve this part of the formula, we only solve this part first, which is integral 1 to infinity of 1 over x. The way we solve this part of the formula, we use limits, which a as infinity, and rewrite the formula as integral 1 to a of 1 over x dx. Since integral 1 over x dx equals to ln x, we can get the limits a as infinity of ln a minus ln 1, which equals to infinity. Since square root of 1 plus 1 over x 4 square bigger than 1, so 1 over x times square root of 1 plus 1 over x 4 square bigger than 1 over x, because bigger of the x of 4 square makes the 1 over x 4 square smaller. Finally, we can get 2 pi integral 1 to infinity of 1 over x times square root of 1 plus 1 over x 4 square equals to 2 pi times infinity, which equals to infinity. Let's take a look at next questions. Rotation around x-axis of y equals 1 over x squared, which x bigger than 1. First thing first, write down the formula we need. S equals integral 2 pi fx times square root of 1 plus dy over dx squared dx. After we put the number we have right now, the formula becomes 2 pi integral 1 to infinity of 1 over x squared times square root of 1 plus derivative 1 over x squared dx. Next step, we solve the derivative of 1 over x squared, and here is how to solve it. Then, since square root of 1 plus 4 over x 6 squared bigger than 1, so 1 over x squared times square root of 1 plus 4 over x 6 squared bigger than 1 over x squared. Just like last example, we only need to solve this part of the formula. So we write down like this: 2 pi integral 1 to infinity of 1 over negative x. And here is how I get the negative 1 over x. We also use limit to solve this formula. We write limits a as infinity of 1 over negative a minus 1 over negative 1, which equals to 0 plus 1 equals 1. And the all formula will becomes to 2 pi times 1, which equals to 2 pi. Let's move on to next questions. Generated by rotating 9x equal y squared plus 18, which x bigger than 2, smaller than 6 about the x-axis. The first thing we do is rewrite the equation to x equals y squared over 9 plus 2. And we know x is bigger than 2, smaller than 6. So if x equals to 2, then y equals to 0. If x equals to 6, then y equals to 6. Next, we write down the formula for surface area, which is integral 2 pi times y times square root of 1 plus derivative f y squared dy. And put our number in the formula. The formula becomes 2 pi integral 0 to 6 y times square root of 1 plus 2y over 9 squared dy. And when we solve the formula, we can simply get this formula, and we can get our answer, which is 98 pi over 3. The last question is finding the surface area for x equal 3 times square root of y, which y bigger than 1, smaller than 8. First thing, we rewrite the equation, which is y equals x3 squared, and we know y is bigger than 1, smaller than 8. So if y equals 1, then x equals 1. If y equals 8, then x equals 2. So the value of x is bigger than 1, smaller than 2. Then we can write down the surface area, which is 2 pi integral fx times square root of 1 plus derivative fx squared dx, and put our number in the formula. It becomes 2 pi integral 1 to 2 x3 squared times square root of 1 plus 9 times x4 squared dx. To find this part of the formula, we use u substitution, which let u equals to 1 plus 9x4 squared du equals to 66 x3 squared dx. Then the surface area equals to pi over 18 integral 10 to 145 of square root of u du. And next you guys can solve it. The answer is negative 10 over 3 times 2 square root of 10 minus 29 square root of 145.
Find surface area of r equals 1 plus sine theta from 0 to pi over 2 when we rotate it about pi over 2 axis, which is vertical axis. When we draw this r graph, looks like this. So when theta is 0, then it's r equals 1. And when it's pi over 2, then it's 2. When it's pi, then it's 1. When it's 3 pi over 2, it's 1. It's 0. So we want to find this segment's radius and arc length. So surface area will be 2 pi times 1 plus sine theta times cosine theta times arc length. To find arc length first, we need derivative of the derivative of r, then square it and add them up, add with r squared. So we can simplify this and then make u substitution, and we get this value with limits from 0 to pi over 2, and we get that value. The next problem asks for surface area rotated about x-axis. When we draw the graph of fx, it looks like this, and we want to find this segment to this segment, the side areas. So we plug in the y value in terms of x,
and then we find the arc length. And so when we find the derivative of fx, this is the value, and when we square it, we get minus 1 over 2, but it'll become 1 over plus 1 over 2, and then we get out of the root with this value. So when you organize it, it looks like this, and you integrate here, plug in the limits, and we get about 25. Okay, the next question is surface area of the region inside of R1 equals 2, outside of R2. So when it comes to surface area, inside, outside is the same because they don't have a volume. It's an empty. It's gonna be empty sphere, and this gonna be empty sphere. So they don't have any overlapping area, except for this point. But this point, in terms of area, doesn't have value. So we simply need to add those two surface areas. And each radius will be 2 sine theta and 2 cosine theta sine theta. Let's look at surface area of R2. Then we plug in 2 cosine theta sine theta, and the arc length is easy to find because the derivative of R2 is sine theta and R2 is cosine theta, so they become constant when they're squared. So we organize this, and we need to make u substitution, and we get this value. And when we look at R1, it's much easier because R1 is constant and becomes 0 when it's derivative. So it's easy to calculate, and we get 20 pi. The next part we are going to look at is finding the intersections between parametric equation and line. Parametric equation is in terms of x, y, and t. The line is in terms of x and y. So what we need to do is to find the intersection, and then which is in terms of x and y, and then we find t by plugging the parametric equation into line equation. So line L passes through this point, and circle C is in terms of t. So what we need to do is to get the path of circle C, and to get the path of C, we need to get rid of t. So we move this 1 to here and square these 2 and add x squared plus y squared. And the L equation is y equals square 3 minus 1 x plus 1. When we draw the graph, we see these intersections. These are x comma y. But what we need to know is the t, which is an angle. As you see, t is a value of radian. So t goes from here and goes circle and then come back. So t is this angle, and when t becomes this angle, they intersect. And when t becomes this angle, they intersect. So in the range of 0 to 2 pi, we need to find these 2 points and the two t values. So to find the t, plug back the parametric equation into the L equation, the line equation. And then we can simplify by making a tangent t, and which equals to 0.732. So when we get inverse of tangent, we will get the t-value. But we need to know that the tangent graph repeats every pi value. So when t is here, then it'll be tangent t. But this will be t plus pi, and it'll have same value as tangent t. So as long as t is less or equal to 2 pi, we need to find the second t, which is here, 1.2011 pi. So you can easily guess this is 0.2011 pi, and this angle is 1.2011 pi. So when we plug in each t value into the circle C equation, then we get the intersection points in terms of x and y. So this is 0.807, 1.59, and this point is negative 0.807, 0.409. So as you can see, because the line passes the circle, the intersection of the circles will have the symmetric value of x. So this distance and this distance should be same. And the follow-up question is to find the slope of the intersection point. What we want to know is at this point, what is the derivative value? So we need to find the derivative of y, which is dy dx. dy dx will be this slope. But as you can see, because the line passes the center, it will have the symmetric value, which have the symmetry slope. So to find dy dx, we need to make it in terms of dt. So we divide each numerator and denominator by dt. And dy dt becomes sine t's, dy dt becomes cosine t, and dx dt becomes minus sine t, which gives us the negative cotangent t. So to find the derivative of that intersection point, we need to plug in the t value. So when t is 0.2011 pi, then the slope will be negative 1.366, and the other t's slope will be same as the same value,